All right, let's dive right in. Today, we're going to talk about the fundamental force that literally builds our world, from the water you drink to the very air you're breathing. We are getting into the absolutely incredible world of covalent bonding.
I mean, it's a huge question, right? Have you ever just stopped and wondered what's the invisible glue holding everything together, from a super hard diamond to a simple drop of water? Well, the answer lies deep down at the atomic level, in a kind of powerful partnership. And there it is, the covalent bond. Now, this isn't about one atom giving away an electron and another one taking it like we see in ionic bonding. No. This is a team effort. It's a cooperative venture, a sharing agreement between nonmetal atoms that creates the molecules essential for, well, everything. But why do atoms even bother doing this? What's in it for them? Well, it all boils down to one universal atomic desire, the quest for stability. Think of it like this. The noble gases on the periodic table, neon, argon, they're the VIPs, the cool kids. They have full outer electron shells, which makes them super stable and, frankly, a little aloof. They don't react much. All the other nonmetal atoms, they want to be just like them. So they team up and share electrons to get that same stable, complete outer shell. So how does this sharing actually happen? The best way to picture it is like a handshake between two atoms, where the hands they're shaking are their electrons. But just like in real life, not all handshakes are created equal. We've got three main types. A single bond is your basic handshake, just sharing one pair of electrons. A double bond? That's like clasping two hands together. They're sharing two pairs. And a triple bond? Now that's the tightest grip possible, sharing three full pairs of electrons. That's what holds the super stable nitrogen gas in our atmosphere together. And here's the key takeaway from all that. The more electrons you share, the stronger that bond becomes. As you go from a single to a double to a triple bond, that handshake gets tighter and tighter, pulling the atoms closer together and making the bond much, much stronger. Okay, so representing these atomic handshakes is obviously super important for chemists, but how in the world do you draw something that's impossibly small? Well, there are a couple of standard ways to do it. First up, you've got your dot and cross diagrams. These are really useful because they show you exactly which atom each electron originally came from. But for a quick and dirty approach, chemists usually go for displayed formulas, where one simple line represents one shared pair. It's clean, it's fast, and it gets the point across. Now let's see what these bonds can actually build. See, covalent bonding doesn't just make one type of thing. It actually creates two completely different families of substances. Tiny, simple molecules and absolutely enormous, giant structures. And this right here is the critical difference. In simple molecules, like a water molecule, the covalent bonds inside it are super strong, but the forces of attraction between one water molecule and the next, those are pretty weak. Now in giant structures like diamond, it's a whole different ballgame. Everything is locked together in one continuous, super strong web of covalent bonds. So because those forces between the simple molecules are so weak, it doesn't take much energy to break them apart. And that's exactly why they usually have low melting and boiling points. Think about how easily water turns into steam. And since there aren't any free-floating charged particles, they're not going to conduct electricity. Giant structures are the total opposite. Take diamond. Every single carbon atom is bonded to four others in this rigid 3D network. If you want to melt it, you have to break countless, incredibly strong covalent bonds, and that takes a massive amount of energy. Now, graphite is the interesting exception. Its atoms are in layers that can slide past each other, which is why it's soft enough to write with. And it has free electrons between those layers, making it the only giant structure that can conduct electricity. So far, we've talked about this sharing as if it's always perfectly fair and square. But in the atomic world, just like in ours, sharing isn't always equal. And this leads to a really cool concept we can think of as an electron tug-of-war. So what happens when one atom in the bond is a little bit greedier for those electrons than the other one? It completely changes the character of that bond. This lays it out perfectly. In a nonpolar bond, that tug-of-war is a perfect tie. The electrons are shared right down the middle. But in a polar bond, one atom has a much stronger pull on the electrons, a property we call electronegativity. It yanks those shared electrons closer to its side of the bond. And this unequal sharing has a huge consequence. It creates these little partial charges. The atom that's hugging the electrons gets a slight negative charge. We show that with a delta minus symbol. And the other atom is left with a slight positive charge, a delta plus. A classic example is hydrogen chloride, where that greedy chlorine atom pulls the electrons away from hydrogen.
Now, this whole idea of polarity is incredibly important. Why? Because those slight positive and negative bits on molecules cause them to attract each other. These are what we call intermolecular forces, and there are three main types that basically dictate everything about a substance, like its boiling point.
Here we can see how they stack up. At the weakest end, you've got van der Waals forces, which exist between all molecules. In the middle are dipole-dipole forces, which happen between polar molecules. But the undisputed champion of strength is hydrogen bonding. It's an extra strong type of dipole-dipole force, and it's the reason water has such a high boiling point and, makes life on Earth possible.
Okay, we've been through a lot of the science, but why does any of this actually matter to you? Well, because these bonds aren't just something in a textbook. They are literally the architects of your everyday reality.
I mean, just think about it for a second. Water, the oxygen you're breathing right now, the carbon dioxide plants need, the natural gas that might be heating your home. All of these are simple molecules held together by covalent bonds. The properties we depend on every single second are a direct result of how their atoms decided to share electrons.
This quote really just hits the nail on the head. Understanding these bonding types lets us understand why some stuff is hard, some stuff is soft, why some things are liquid and others are gas. So to wrap this all up, let's do a quick side-by-side showdown with that other major type of bonding, ionic. This table is a fantastic summary. On one side, you have ionic bonding, a metal plus a nonmetal, where electrons are transferred. This creates a giant lattice with a high melting point. On the other side, you have covalent bonding, two nonmetals sharing electrons, usually creating simple molecules with low melting points. Just two different strategies to get stable with totally different results.
And that's where we're going to leave it today. These simple, almost elegant rules of sharing electrons have built the entire biological and chemical world as we know it, from water to DNA. It really makes you wonder, doesn't it? As we get better at understanding this, what new materials, what new molecules with incredible properties are we going to design next? Thanks for tuning in.